Okay, so let's talk a little more about the energy involved in forming a solution. So we can think of solution formation as happening in 3 steps. So the first step, we have our solute particles, and they're going to have to separate from each other. So like if this is a sodium chloride, the sodium ions and the chloride ions are all stuck together by their ionic bonds, and in order for them to dissolve in the water, they're going to have to get away from each other. So this is always going to be endothermic, because in order to separate these particles, we have to put energy in to break up whatever force is holding them together. So for some things, this will be much larger than others. Some will be very easy to break up, but there still requires some energy. So we can call this the heat of solute, meaning the heat required to separate the solute particles. This is always going to be greater than 0. We need to do a similar thing with the solvent particles. So if this is water, we'll say, in order for our solute to get into the water, we have to separate the water molecules, right? Otherwise, there's no room for the solute particles. So separating these particles, disturbing their intermolecular forces, is also going to require us to put energy in. So we call this delta H solvent, the heat needed or energy needed to separate the solvent molecules, and this will also be greater than 0. So we've separated all the particles. Once we have the solute particles separated from each other and the solvent particles separated from each other, then we can bring them together and let them mix. So when these 2 groups of separated particles come together, now they're going to be attracted by their intermolecular forces, right? And so this is a lot like the lattice energy, where we had our ions in an ionic compound coming together, and there's a lowering of energy, there's a release of energy when that occurs. So we call this delta H mix, the energy in mixing these 2 together. This is always going to be exothermic, because as the particles interact, they're going to release energy. So we have 2 steps that require us to put energy in, and 1 step that gives energy back. So the enthalpy of solution is the sum of those changes. Separating the solute, separating the solvent, and then mixing them together. The overall sign is going to depend on the relative sizes of these, their magnitudes. So solution formation can be endothermic or exothermic. It can absorb energy or release energy. In an exothermic solution formation, here we're starting with our pure solvent and our pure solute. And we have to separate the solute particles. That requires us to put energy in. And then separating the solvent molecules requires us to put energy in. And then when we allow these to mix together, we get a release of energy. In an exothermic solution formation, the release of energy here is greater than the sum of energy that we had to put in. In an endothermic situation, we separate the solute, we separate the solvent, but when we mix these together, it does not release as much energy as was put in to separate them, and so the net result is that this absorbs energy from the surroundings. Delta H would be positive, delta H solution. Yep. So, talking now just about aqueous solutions. Here we have our equation. The enthalpy of solution is equal to the energy change separating the solute particles plus separating the solvent particles plus mixing them back together. So we've got those 3 terms. We often combine the solvent and the mixing terms and call this the heat of hydration. And so that's taking separated solute particles and putting them in water. It's the combined separating the water molecules and the energy released by mixing. For ionic compounds in water, this is always going to be negative because the delta H solvent is breaking up hydrogen bonds between the water molecules, and those are fairly strong on the scale of intermolecular forces. But the mixing, what we've got happening here is we have the formation of ion-dipole interactions. And ion-dipole interactions are much stronger than hydrogen bonding. So what we're breaking is weaker than what we're forming, and so the net result is that this is negative. Delta H solute is always going to be positive, and so here again, the sign of this could be either positive or negative depending on the magnitudes of those two terms. Yeah?
Okay, so what was the mix?
The mix is, delta H mix is where we've got the separated solute particles and the separated solvent particles, and we mix them together. And that's always going to release energy because there's attraction between them. Yeah.
Can you go back to the slide 17? Can you explain?
Yes, I can explain this again. So here we've got our solvent and our solute, pure substances in their own beakers. In order for these to mix, and this is essentially a Born-Haber cycle where we're imagining things happening, and we can do that because these are all state changes, and so what matters is only the starting point and the ending point, not how we got there. So this is like all those other things that we drew. So we can imagine, well, what happened? Come on, pointer. What has to happen in order for these to mix? Well, we have to separate the solute particles from each other so that the solvent particles could get in there. And that's going to require us to put energy in, because these solute particles are attracted by some type of intermolecular force, right? So to break that intermolecular force, we have to put energy in. And then to break up the solvent, to separate it, we also have to put energy in. So now we've got separated solvent and solute particles, and when we mix those together, they're going to be attracted to each other. Those might be just dispersion forces, relatively weak, but it's still giving off energy. Or they might be strong, like hydrogen bonding. They're really, really attracted to each other, and they're going to snap together, right? But as these mix, it will release energy. So this is an investment. We have to put energy in to break up the solute, put energy in to break up the solvent, and then we get a payoff when they mix together. In an exothermic process, the payoff is greater than the investment. And so the result is that the solution feels warm when it mixes. It gets warm because energy is being released. The opposite, here we have to break up the solute, we have to break up the solvent, but here, when we mix them together, that force of attraction between these particles is not as large, and so the release of energy here is smaller than what we had to put in.
I don't know if it's going to be larger or smaller.
That's a great question. How do you know if it's going to be larger or smaller? That's hard. And I would not expect you to be able to do that. There's a lot of factors, right? If you had to identify that in a question, there would be other information given, like that the solution felt warm to the touch or cold to the touch, something like that. Or we could give you actual numbers and you could add them up and see what the result was. Yeah. Anybody else have any questions? Why would an endothermic process like this happen at all if it's not a lowering of energy? Entropy. So this tendency towards mixing is another factor that drives things. So if this increase in energy, potential energy of the system is only small, it may be more than offset by the increase in entropy. Yes?
Right? Not just the endo.
The endothermic one, our mixture is at a higher potential energy than our starting components. Here, our mixture is at a lower potential energy. It's gone down in energy, and the reason it releases energy is because as it goes down in energy, the energy has to go somewhere. It's going to go into the surroundings. Well, the energy of the solvent and the energy of the solute are spreading out, but that doesn't show in an energy diagram like this.
So you're saying only V is entropy?
Pardon me?
You're saying only V is entropy?
No, entropy plays a part in both of them.
Oh, okay.
Yeah. Yeah, entropy is increasing for both of them.
Okay. I thought you were just saying.
But this one, we can't understand just in terms of energy changes. This one we could understand without the concept of entropy because, oh, well, of course it's going to happen. It's a lowering of energy. Sure, that's natural. But why is this one happening? The energy's going up. How does that work? Well, it's because the entropy is increasing and that offsets that increase in energy. We talk a lot more about that in Chem 1B. So we won't get any farther than this with the idea of entropy. So this delta H solute, that's the energy needed to separate the solute particles from each other. If we're talking about an ionic compound, that's the same quantity as the lattice energy, just in reverse. So for, I guess this is potassium fluoride, the lattice energy is the energy when these two ions in the gas state come together to form the solid. That's the lattice energy. So to separate those ions, here we have a solid and we're separating the ions. That is the same energy as the lattice energy, just opposite in sign. So delta H solute is equal to negative delta H lattice for ionic compounds. So we've got two terms here. Our overall equation here is the heat of solution is equal to delta H solute plus that heat of hydration, which is the mixing and the separating of the water. So if delta H solute is smaller than the heat of hydration, then the process is going to be exothermic. This is a small positive number and a large negative number. This sum is going to be negative, releasing energy. If delta H solute is greater than the heat of hydration, if we have a large positive number and a small negative number, then the heat of solution will have a positive energy change. It will be endothermic. The solution will feel cold because it's pulling energy in from the surroundings. It's actually not as rare as you think. So if you go to like CVS or something, you can buy these little instant ice packs, right? Or if you have a first aid kit, there might even be one in that first aid kit. There's a little instant cold pack, right? And you squish around, you break something inside, and you mix it, and it gets cold. How does it do that? It's an endothermic reaction of mixing. So not super common, but not as rare as we might think.